Today we're going to speak about polarization. And this is a phenomenon that relates to light and has many practical applications, for example, in 3D cinema or in things like LCD screens. So we will briefly discuss what it is, how it comes about, and, well, why it's so useful in our everyday lives. Now, before we start talking about polarization, we need to talk for a little bit about electromagnetic waves. Now, remember that a wave is just a perturbation that propagates through space. So it's something like this, and it's normally moving in some direction. And you may also remember that there's two types of waves. There's longitudinal waves, where the perturbation is in the direction of motion. So, for example, like in a spring or sound waves. And then there's transverse waves, where the perturbation is perpendicular to the direction of motion. Now, light is a transverse wave. In light, what's propagating is an electromagnetic field, E. And this electromagnetic field is oscillating, so it goes up, down, up, down, up, down. And all the while, the wave is propagating perpendicularly to this field. So the wave is going this way, and the field is going this way. Of course, we live in a 3D world, so this is not an accurate picture. This would look something like this, right? So we would have many different possibilities for E to be at. So it could be anywhere in here, and it could do this or this or this, anything that's perpendicular to the direction of motion. So what does it mean for a light wave to be polarized? Well, normally when we get light from the sun, what we get is a bunch of waves, and each one has the E in a different direction. So some of them have the electric field going like this, some of them like this, some of them like this. It just goes all over the place. Okay, this is called unpolarized light. However, what I can do is filter this. I can put this through something called a polarizer, and a polarizer is a little bit like a filter. Okay, you can imagine it. It's not really the way it works, but it's similar, like a slit that will only let some of the components, for example these ones, of the electric field to go through. So that after this goes through, all we're left with is an electric field that goes like this. So oscillates only in this plane, because all the other components have been cancelled by the filter. Now this is polarized light. It's light that oscillates only in one direction, in this case like this. We could, of course, this is horizontally polarized light. We could, of course, have vertically polarized light if we just, rotated this filter 90 degrees. Now remember, when we did harmonic motion, we found that the displacement, let's just call it x, was equal to some amplitude times cosine of wt, right? Now in the case of a wave, we can also define some kind of displacement, and it looks something like this. Probably x is not a very good name, because I'm going to use it again, but it looks something like cosine of wt minus chi x. And don't worry, because you don't need to know this formula. What's important here is that this perturbation, it has an amplitude, right? And in the case of an electric wave, well, an electromagnetic wave, this amplitude is actually our electric field. So what we have is that our electric field is just some E0 cosine of some stuff. And this just means that the perturbation depends on time and also on space. Okay? But what's important here is that the role of the amplitude is played by the field. Now, if you remember anything about waves in strings and stuff like that, you'll remember that the intensity of a wave is proportional to the amplitude squared. And therefore, the intensity of an electromagnetic wave is going to be proportional not to the electric field, but to the electric field squared. And that's basically what we're interested in. We need to remember that when we're talking about electromagnetic waves, if we know how big the electric field is, then the square will give us the intensity of the light. And we're going to use this to derive this law called Mitosis Law that will tell us the intensity of polarized light going through another polarizer. Now, in order to do this, all we need is some very, very elementary trigonometry. So imagine that I have some light that's already polarized this way. And it's going this way through a polarizer. And this polarizer wants to polarize it to a certain angle. So here's our polarizer, and it makes a certain angle theta with the incident light. Now, what's going to happen is that, of course, out of all this light, only the one that's parallel to our polarizer is going to survive, right? So let's just make a little triangle here. So here's our polarizer, here's our light, and only the part that's parallel to the polarizer is going to survive. So let's calculate this. Well, that's just multiplying by the cosine, right? So we've got that the surviving E is going to be equal to the E that we had at the beginning. Let's just call it E0. And remember that E is the electric field, so E0 times the cosine of theta, right? But remember that the intensity is proportional to E squared. So this means that the intensity has to decrease by E0 squared cosine theta squared. And of course, this is just the intensity we had at the beginning here. So we can just write this down as the intensity at the beginning times the cosine squared of the angle of the polarizer. And this is called Mitosis Law. It just tells us that whenever polarized light goes through a second polarizer, the intensity is proportional to the square of the angle between the polarizer and the light. And this makes sense, right? Because if theta is 0, then that's I0. It means that, well, of course, all the light is in the direction of the polarizer, none of it gets lost. If theta is 90, means that none of this will go through, and therefore I will have 0 intensity. Now, this is actually very handy because I can use this to analyze light. So instead of a polarizer, what I have is something called an analyzer. And the idea is, imagine that I have some light, and I have no idea whether it's polarized or not. I don't know. Well, if I use a polarizer and it's not polarized, what's going to happen? Well, what's going to happen is that on average, I'm going to get 50% going through, right? Because this has every possible orientation, and on average it's going to be something like this, and of course I'm going to get 50% of this wave going through. So if this is polarized, no matter how I put my polarizer, I'm going to get 50% of the light going through. Sorry, this is not polarized, of course. Now if this is polarized, however, in a certain direction, then depending on how I orient this, I'm going to get different intensities. And I can very easily figure out how this is polarized, because when I get the maximum intensity, it means that the angle is the same. When I get the minimum, it means that the angle is 90 degrees. So I can use a polarizer to figure out whether the light that I got is polarized or not. When I do that, I don't call it a polarizer anymore, I call it an analyzer. Now, here comes a part that I find particularly hard to understand, but bear with me for a while and hopefully you'll get it too. I found it hard personally. Imagine that I have some water, for example, here. So this is the surface of the water, and here's this water, and there's a ray of light that's incident on the water. Okay, and now the light here is not polarized. Well, it's all over the place. Okay, now remember that the electric field is always perpendicular to the propagation of the wave because it's a transverse wave. Okay, so this could be anywhere in the polarization plane, in the plane, but not this way. Okay, now let me just draw this. So this could be any way like that, but again, it doesn't go this way. Okay, and now I ask myself what's going to happen to this thing once it touches this surface, what's going to happen to the refracted ray, and what's going to happen to the reflected ray in terms of polarization. Now, in order to do this, first I need to know what's going on in the water. And what's going on in the water is that we have these little molecules, electrons and things like that, that will vibrate following the electric field in the same direction as the electric field. So if this is vibrating this way, then the electrons here are going to vibrate this way, and then they're going to transmit this same wave in the same vibration. So the electrons, all they do is they vibrate in the same way of the electric field and transmit this vibration to the following electron and so on, so that this gets transmitted this way. What they cannot do is change the orientation of whatever's coming their way. Okay, so I ask myself, okay, so how is this going to go over here? Well, the electrons are going to vibrate like this, following this, but of course all the components that are not perpendicular to the propagation of the light are going to get lost, right? So I get something like this. Imagine that my electrons are vibrating like this, but of course that's not perpendicular to the light, to the propagation of the light, so only these components here are going to survive. Okay, so where are the other ones going to go? Well, the other ones are going to go to the reflected ray. But again, this will only happen for the components of this that are perpendicular to the propagation of the reflected ray. So some of this, not all of it, so some of this. So if I draw this, so let's just take this thing here, and I draw it here. So let's just say that this part here is going to go to the reflected ray. Now notice that this is way smaller than this, which means that this will be partially polarized in the direction that goes in and out of the plane, because this is very small, right? So this gives us an idea. What if I could make this infinitely small, so that there was no component vibrating in this direction? Then I would have waves that would be polarized in the direction in and out of the screen. And then I would have polarized waves coming out. And that's the idea that Brewster had. And what he called this is, well, there's actually an angle of incidence that will give you this polarization, and this is called the Brewster angle. Now, how can we do this? Well, it's actually pretty simple. All we need to think about is, okay, so the plane of polarization of this is this, right? This cannot go anywhere else but in this plane. It cannot go down. Therefore, my electrons are going to oscillate in exactly this direction. And now I ask myself, okay, so let's project this in here. And now all of this will be polarized light. How can I make this in such a way that the projection in here is zero? Well, if this is actually parallel to this, then there will be none of this, right? And how can I make this parallel to this? Well, if these two guys are perpendicular. So let me show you. Here I got my surface. Here I got my normal. And I don't know how my incident rate goes, but imagine that this is like that, and this is like this, and this is 90 degrees. Okay? Now, if my electrons are vibrating this way, as you can see, once I put this over here, what happens? Well, what happens is that there's no perpendicular component to this, and therefore all the light that's coming out has to be polarized like that. So this is coming in and out of the screen, but it doesn't go to the sides. Now, the angle of incidence that's going to give us this is called the Brewster angle. So the idea is we want an angle such that it's going to give us a 90-degree angle here. Now let's see if we can calculate that. Now I'm going to call this theta r. That's theta b for Brewster, and then all I'm going to do is to apply Snell's law. So you hopefully remember that n1 sine of theta 1, in this case theta Brewster, equals n2 sine of theta 2, in this case theta r. Now we know that the law of reflection holds. What does that mean? Well, the law of reflection says that this is also theta Brewster, right? Because the angle of incidence is equal to the angle of reflection. And we know that this is 90. So therefore we know that this is 180 minus 90, that's 90, minus theta Brewster, that's the angle of reflection. So we can change this thing here by 90 minus the Brewster angle. So what really we get is n1 sine of the Brewster angle equals n2 sine of 90 minus the Brewster angle. But then we're like, oh, but that's just the cosine of the angle. So then we can rewrite this as n1 sine of the Brewster angle equals n2 times the cosine of the Brewster angle. And then we're pretty much done, right? All we need to do is just put this here to turn it into a tangent, and then we get sine of theta Brewster over cosine of theta Brewster equals n2 over n1, and that's of course the tangent of the Brewster angle. So, summarizing, tangent of the Brewster angle equals n2 over n1, which means that if we project our light at this angle of incidence, our reflected light is going to be polarized. Ain't that handy? Now I'm happy to announce that the math is over, but there's some applications that we can consider. So imagine that I have some light that's not polarized, and I send it through a polarizer that polarizes it horizontally, so now my light is like that. And then after a while I send it through a vertical polarizer, and of course what's going to happen is that I'm going to get no light. However, what I can do is place a sugar solution here in the middle. And if I do this, what's going to happen is that after this polarizer, I'm going to get some light. And the question is why? What does the sugar do to my light? If this was polarized this way, then there should be no light here. So this must be changing the orientation of my light. This must be doing something to my light. It must be rotating the oscillation of my light. And that's exactly what sugar is doing. Sugar is something that's called an optically active material, and what it does is it rotates the plane of polarization of my light, which makes it capable of going through the second polarizer. And it turns out that there's many materials that can do this. So for example, we will probably do an experiment in class where we get a protractor. Is that a protractor? Well, a protractor or a ruler or whatever. And that's made of plastic. And then we put a polarizer on top and a polarizer under at 90-degree angles. And what's going to happen is that if you stress the plastic, you will get, funny looking colors and whatnot. And that's because this is not an optically active material, but when you stress it, it becomes one, and it allows the light to go through. This allows us to analyze stress in structures and things like that. It's very, very handy application. We can also use this property of rotating the polarization angle for measuring the concentration of a solution, right? So because if I have very little sugar here, then I'm going to get very little light going through this. If I have a lot of sugar here, then I'm going to get more light going through this. So the amount of rotation of this light is going to be proportional to the amount of sugar here. And apart from this, I can use this property to make LCD screens. LCD, you may know, stands for liquid crystal display. So an LCD screen is based on polarization and optical activity. What we got are these liquid crystals which are made of these molecules that are very thin and that rotate, well, not the molecule itself, but what they make is they make the electric field oscillate in the same direction as they are. Okay, so I have this liquid crystal here, and what I do is I place this liquid crystal between two pieces of glass. Now, in the first piece of glass, I make very small 1 nanometer dents that are in this direction so that the glasses will align themselves with this. In the second glass, I make also very small dents, but 90-degree angle so that the molecules will align themselves with this. So what's going to happen in between? Well, in between, because these molecules are slightly attracted to each other, what's going to happen is that I'm going to have a molecule like this, and then the next one's going to be a little like this, and the next one's going to be a little like this, until I get to the 90-degree angle. So now what happens if I put one polarizer here and one polarizer over everything? Well, what's going to happen is I'm going to get, so let's imagine that the first polarizer polarizes light vertically and this one polarizes light horizontally. What's going to happen is that, okay, have some light coming in like this, then it starts oscillating like this, and then it gets turned a little bit by the next one, and then turned, and then turned, and then turned, and then turned, until it's oscillating like this. Now, when it's oscillating like this, it comes out through the second polarizer, and you can see. So this whole setup is transparent. However, this only happens if these little crystals are placed in exactly this configuration. So what I can do is generate a little electric field that will force these molecules to change their orientations. It doesn't really matter how, because once they're not in this shape and they're like all like this, or all like this, or even all like this, it doesn't matter anymore. What's going to happen is that no light is going to go through, and I'm going to have a dark pixel. So basically, if I can control this electric field, I can control which pixels are transparent, which pixels are not. I place a little mirror here, and then sun comes in, and if there's no electricity here, this just comes in and out. If there's electricity here, dark pixel. And I can use this to make displays and show numbers and whatnot. I can make this even cooler if I introduce color filters in some pixels, and then what I have is an LCD color screen, which is, well, probably the screens that you have at home right now. Alright, so that's it. You hopefully now know what polarization is, you know how it works, you can calculate the intensity of polarized light, and you can also calculate the Brewster angle, and on top of that, you know some applications. Now it's time to do the problems. There's lots of them. They're not easy. Good luck.